Okay, yeah, let's start the recording. Great. So welcome to our session. I hope you are well and you are ready to discuss more modeling techniques today. So last week we made an introduction to modeling. We basically discussed the main idea of decision trees, which is also used for feature selection, the method information gain. And then we connected to decision trees, and during our workshop we actually implemented a simple decision tree. So today I am going to continue to discuss modeling techniques. So we are at the modeling stage of Christian methodology, and we will mainly focus on linear models today. And I will briefly recap on the decision trees, since we will also discuss one of the other properties of these models. And then I will describe the linear classifiers in general. We will focus on SVM and logistic regression, and we will also implement these techniques during our workshop next week. And if we have time at the end of the session, we will make an introduction to overfitting problem. Okay. So you may remember this example from our workshop this week, either on Monday or Tuesday. As you may remember, we can actually illustrate all points in our data set on a graphical space. And here we have age and balance. And assume that these are the two features, and default is our target variable. And the points here, the data points, are actually classified based on the outcome, either default or not default. And just as a quick reminder, this was a credit application. If the applicant didn't pay it back, they are registered as default. If they pay it back, they are registered as not default. And any data point from our historical data can be represented on this graphical space. And with the decision trees, what we do, we start with this entire data set where we have complex mixed outcome. So as you see in here, we have a high entropy. Both default and not default cases are quite present in our data. We can't make good predictions. That's the reason we use features from our data set to make a prediction. And in the decision trees, we start with let me also have my pen. Okay. In decision trees, our root node actually is the entire data, and then by using the features from our data set, we split it. Overall idea is to decrease the entropy as we split more as we go forward. And at the leaf nodes, as you see in here, we make a prediction, and this prediction is one of the outcomes, either default or not default, based on the majority. So here, for instance, we divide the decision tree first with respect to balance and then with respect to age. So this is where we have balance less than 50K. And this whole part is balance greater than or equal to 50K. And this area is also divided with respect to age. And as you see here at the child nodes or at the leaf nodes where we make a prediction, we have these samples. So some of the data points actually end up in these leaves. And then when we make a prediction, we actually consider the majority. So here we have 7 default points and 3 not default points. Overall, we have 10 samples, 7 of them from default. Therefore, our prediction is default. So this is the default prediction, as you see in here. And at the other leaf node, we have pure outcome, and all of them are from not default, and we predict as not default. And when the balance is less than 50K, as you see in here, majority is the default cases. Therefore, our prediction is default. So when we split the data at the leaf nodes, we actually have some of the samples from our data set. And when we make a prediction, we consider the majority. This is how decision trees work. They can either return the class prediction directly, as you see in here, default, not default, or they can return the probability estimation. So these are called probability estimation tree. So they can both return probabilities. On top of it, they can return the class predictions. So how these probabilities are calculated? It is very simple. We actually count the samples. So in here, overall, we have 20 samples, and 2 of them are from default, 18 of them are from not default. Therefore, the probabilities for default is 18 over 20, and probability of not default is 2 over 20. So overall, we have 20 points, 20 samples. On the other hand, when H is less than 45 and when H is greater than or equal to 45, so can you estimate the probability of each? Do you have any recommendation? For instance, what is the probability of not default when H greater than or equal to 45? Any idea? So here, we only consider the points at this sample, at this split. So these are the points when H is greater than or equal to 45 and balance is greater than or equal to 50. So I see one, that's correct. We only have not default cases here, therefore probability is 1. On the other hand, when H is less than 45, what is the probability of default and not default? So for default, how many cases we have? For 7. Overall, we have 10 points. And for not default, we have 3 over 10. So probability estimation tree basically checks the number of samples at the particular leaf node. And then when calculating the default, not default, it basically checks the proportion of each outcome. Okay, so these are the same writing. When we plot our tree or when we build our tree in Python, we can actually ask Python to return the probability estimations. So there is one question why we didn't include whole. At this stage, we already split with respect to balance. So we are considering after the split. So we don't consider the whole, we consider after split. And then at this leaf node, overall, we have how many node points here? 3, 6, 7, 10. 10 samples, and here we also have 10 samples. So we consider the number of samples at the leaf nodes when we estimate the probabilities. Since this leaf node actually shows when balance is greater than 50K and H less than 45. So under these conditions, we actually calculate the probabilities. That's the reason why we consider the samples at each leaf node. I hope this is clear. Okay. So decision trees can both return estimation probabilities and also class prediction. For that reason, they are quite useful, since when you make a class prediction, it will tell you what is the probability of being in that class. In all machine learning models, we use some type of decision boundary. And in decision trees, decision boundaries are, for instance, this one is a decision boundary, and this one is another decision boundary. So decision boundaries help us to actually classify the outcome, like fraud, not fraud, cancer, not cancer, or churn, not churn. Or if you have 3, 4 multiple outcomes, it can help us to divide the data, and based on this division, we make the class prediction. So decision boundary can be either a line, curve, or a surface if we have higher dimensions. Here we have only 2 dimensions, therefore they can be either line or curve. And their main idea is to separate the predicted classes. So based on this separation, we make a prediction. And we are discussing classifier methods now, like we have a categorical output to predict, and every classifier is actually divide the whole data space. We call it feature space, where we have our points in here. These are coming from our data. They divide the feature space so that similar points fall into the same region, and we make use of that region to make a prediction. As you see in here, at this particular space, we are going to predict as not default. So we divide the whole feature space, data points, into smaller groups in here. So this is, let's say, this is group 1, this is group 2, and this is group 3. So we have 3 groups, and after dividing to 3 groups, we focus on each group separately, and if we have a sample falling into that particular group, we predict the class of that sample based on the majority. So decision boundaries in linear classifiers in decision trees help us to identify the segments in our data, and we use those segments to make prediction. Decision trees have these box-shaped cuts like this one. We have boxes in here as you see. So this is another one. And this is the group 1, group 2, and group 3. Linear models, on the other hand, today we are going to discuss general linear models. They use a straight line. Okay. So how the decision boundary is formed? In decision trees, actually, they are formed based on the features. We come up with some categories to classify those features, like balance is greater than 50K, age is less than or equal to 45. So we use the data set itself to identify the segments for a particular feature, and then use those like a rule to decide on the decision boundary. Due to this separation, like simpler rules, it splits the entire feature space, or as you see in here, data space, to rectangular regions like boxes. And this is quite simple, like we have 3 separation in here, but the problem is that as we continue to split, or as the decision tree grows deeper, during our workshop we discussed this, like maximum depth, as we continue to add layers, the boundaries becomes very, let's say, fine, and they start to overlap. So here we have a kind of small example. This is a very big decision tree where we continue to split. And as you see in here, decision boundaries now, some of them only includes one sample. Or we can even define a kind of decision boundary which is specific to only one particular case in our data. So we will discuss this problem today, and as you see in here, as we go deeper, we add more decision boundary, and the problem itself, or the machine learning model itself, start to become more complex, more difficult to interpret, or let's say difficult to understand. In linear classifiers, on the other hand, so we are going to discuss them today, but I would like to start with the description of the decision boundary. This is not like age less than or equal to 45 or balance greater than 50K. In linear classifiers, decision boundary is a straight line, and it is a combination of the features. So here X is our features, such as age, balance, or let's say gender, and so on. So these are the features from the data set. And we obtain this decision boundary as the combination of these features. We don't need to use all of them. We only use the informative ones, or the ones which help us to make a prediction about the outcome. But the overall idea is to find a straight line or a plane. Since these are linear models, their decision boundary is a line shape, which is a combination of the features from our data set. And we use this decision boundary to make a prediction. So how do we make a prediction? We check if a point is on the other, let's say, on the right-hand side of the decision boundary. Here we have more blue points. Our prediction would be class blue. So predict class, let's say, blue. And if the future test point is under the line, here we have only orange points, or the majority is the orange, we predict class orange. Okay, so in the decision trees, we use the features individually, like age, balance, gender, female, male. So we split the data. On the other hand, in linear classifiers, we use the combination of the features to come up with a straight line, and then the straight line is used to make a prediction. If a point is over the straight line, let's say as in here, on the right-hand side, based on the majority, we identify the class. If it is under the line, again, based on the majority, we predict the class. So class here is like fraud, not fraud. This is a classification problem, so we decide on the class of the target variable. As you may remember, we have our data set. Let's say here we have age, we have balance, maybe we have gender. So these are the independent features. We use them to make a prediction. And then we have our target variable. In here, let's say we give an example from fraud. It shows whether the particular record is fraud or not fraud. This is our past data. Let's say this is fraud, this is not fraud. Okay. Let's say frauds are given by the blue dots. This is blue, blue, and this is orange. So how we identify whether a future transaction, customer transaction will become a fraud? We will check whether it is on the right-hand side of the decision boundary, whether it lies on the left-hand side of the decision boundary. Let's say this feature 1 is balance, and feature 2 is age. So these are the points on our space, and as in the decision trees, we illustrate these points. And after we find the decision boundary as the combination of these two features, age and balance, we decide the class, whether fraud or not fraud, based on where they are located. Okay? So I hope this is clear. We will discuss this, how we can identify the decision boundary and how this classification is made. But the main difference between decision trees uses individual features, like we check balance greater than 50, less than or equal to 50, or then we check age less than 45, greater than or equal to 45. On the other hand, in general linear classifiers, we consider the combination of the features, age and balance. So let's look at this in more detail. So linear classifiers also discriminate between classes, like fraud, not fraud, or churn, not churn, cancer, not cancer. So we use this to discriminate between classes, but the model now consider the combination of the features to define the decision boundary. So here you see the equation for the decision boundary. This is a linear equation, and model during training learn these parameters. So they learn this 60 and they learn the coefficient of this 1 minus 0.5. So the learning process, during the learning process, linear classifiers check the features and then try to identify the coefficients of the features to identify or to draw this decision boundary. And some of the well-known linear classifiers are linear discriminant functions, logistic regression, SVM, and we will see some of the examples during our workshop of these models. So how this decision boundary is found? Here we see the example. So as I mentioned, this is basically, these are the coefficients we use to W to show that, coefficients, times features, plus we also have a constant. You can either show it with B or W0. Overall idea during training is to identify these coefficients. Since we know the features come from the historical data. You can consider this process as in the linear regression case if you covered it already in the business statistics module. So we know the features. Given the features, our aim is to identify the parameters so that we can draw this decision boundary, and by using the decision boundary, we can make a prediction. During model building stage or during model training, so during the training time, it searches for the best decision boundary. So it checks the linear combinations of the attributes or features. So these are the features from our data set, like age, gender, balance, and so on. So it checks the combination of these attributes when searching for the best linear decision boundary. And generally, this decision boundary is preferred to be away from both classes. So here we have an example for age and balance again. Let's say this is from our data set and we plotted the points from our data set, records from our data set here. And when we search for the decision boundary, we don't want to be close to one of the sides. This is, let's say this is a linear boundary. Let me draw another one with different color, maybe blue. If we use a decision boundary close to one of the classes, let's say, or group of samples, then we can easily make mistakes. Since currently this is very close to the, let's say, circle in here, and this is our training data, right? We learn from the training data, but we don't know how the real data looks like or how the test data would be, whether it's similar to training data or not similar to training data, we currently don't know. We train the model on the training data. And if the model is close to one of the sites, there's a risk. It may estimate wrongly for the future when we have unseen test data. So here we are very close to the, let's say, circle in here. And in the future, we have a point just lying around here. So if we use this blue decision boundary, this point is going to be predicted as plus, as in these white shapes in here. Or if we use this red decision boundary, it's going to be predicted as a black circle. In order to be safe, or in order to make a better prediction, when we search for the decision boundary, we search for the ones which is generally far away from both regions. Okay, so this whole process, training process, actually is trying to find the best decision boundary to split these two classes. And we can find lots of different ways, actually infinitely many ways to draw this decision boundary. And according to a specific objective, and as we discussed in the previous classes, this objective is to maximize accuracy or minimize error. It is going to find the best separation. Okay. So this is the same example. Here we have age and balance. And as you see here, while model training, our aim is to identify this W2, W1, and W0. This is sometimes shown as B since it's a constant or intercept. Given our data set, age, balance, it checks for all combinations and draw the one or choose the one which help us to minimize the errors made. And what is the errors made? Basically, if you check in here, this is the training data. And let's consider this together. So this is our decision boundary. And let's say we draw this boundary after we train the model. And now we are going to check the errors. And during this training, actually, it calculates the errors and it chooses the decision boundary with the least error. So any points above this line will be predicted as plus. So do you think how many errors we made if we use this decision boundary? For the part which is right-hand side of the decision line, decision boundary. So what is the error on this side? We are going to predict everything as plus, and as you see in here, we are going to miss this point. So error is 1. On the other hand, any point under the decision boundary will be predicted as circle, and here we don't have any error, so error is 0. It doesn't basically count the errors, but there's a function or objective which is based on the number of errors we made. And here we see we have 1 error. So they try to, for instance, if I use this decision boundary, let me find another color, orange in here. Assume that I have this particular decision boundary. Decision boundary 2. So any point over this will be predicted as plus. Any point under this will be predicted as circle. So if I use this decision boundary, now I'm going to make 1, 2, 3, 4, 5 errors. Here we have 0 error since, no, we have also 1 error due to this. We are going to misclassify this one. Under the line, we will have 1 error, but over the line, we will have 5 errors. So we can have lots of decision boundaries to separate these two classes, default or not default, and the one which is actually chosen by the model, learned by the model, is the one with the less error. Okay. The general linear function looks like this. Here, x1, x2, it goes until xn. These are the features. This is coming from the data, training data specifically. And overall idea is to identify what should be W0, W1, W2, so on and so forth, Wn. Okay, so this is the learning part. Given the historical data, we try to learn the coefficients of this linear function. And how does it make a prediction? So once we learn these parameters, as you see in here, so here W0 is 60 minus 60, W1 is 1, and W2 is 1.5. We only have two features, x1 is age, and x2 is balance. So once we learn these W's or coefficients of the model, then for the future time, let's say a customer comes with age, if you consider Jane example from our previous workshop, Jane age was 45 and balance was 60K. So given this customer, we actually put this down into our formulation, equation in here, linear function, and we identify the class, whether it would be over the line on the right-hand side of the line or whether it will fall below the line on the left-hand side of the line. And based on the location where this customer lies, we are going to make a prediction about the outcome, default or not default. So it is important to know our objective when we choose these parameters, W's, so W0, W1, Wn. We are trying to maximize the separation between classes. As I mentioned, we don't want to have a decision boundary close to one of the classes so that in the future, when we make a prediction, there will be a less chance we will make an error. So overall idea is to always minimize the potential errors for the future. As you see, so here we have lots of different ways, and our idea is to find the one which is actually far away from both sides. One question, can we have more than two variables in linear models? By variables, you mean age and balance, or outcome of the target variable like default, not default? Age and balance. Definitely, as you see in here, we have n features. So in our data set, if we have 50 features, we can have a linear model with 50 features. Due to the illustration here, I have only 2, since it's difficult to plot 3-dimensional or more dimensional cases. This is just for illustration. In reality, we will not actually have 2 variables from our data set. We will use more variables, since model learns better when we use more variables. Generally, yeah. Any question about this part? Let me check the time. Okay, if you have any questions, please feel free to type. I would be happy to answer it either during the lecture or after the lecture. Okay. Now, this is the main idea of linear discriminant models. We are going to see how to implement these during our workshop next week. There is one question before going forward. Is it possible that 2 decision boundary makes the same error? You mean 2 different? Yes, it is possible. Then which one to select? So in optimization models, maybe you have covered it. You can have multiple objectives or when you return this, or not multiple objects, but when you return the linear optimization model outcome, there might be more than one optimal solution, multiple optimal solutions. That is possible. It will randomly choose one of them. So you are not going to choose that. The solver or model will return one of the decision boundaries. This is similar to your question, Manu, is similar to the case where we have multiple optimal solutions, which is possible to have. And another question, what about target variables if we have more than two? Definitely we can have a target variable, we have one, but target variable can have more than multiple two outcomes. Let's say we may have a the iris data set is one of the famous ones. So you predict different type of flowers, flower 1, flower 2, and flower 3. So you can have multiple classes, not just default or not default, or fraud, not fraud. We can have a target variable with several categories. And in that case, these linear models generally work as we have flower 1 versus flower 2 plus flower 3. So one of the outcomes is generally the one we would like to predict, and we can group them either coming from that class versus becoming from other classes, one to multiple. So we can do that. Okay. So now let's move to support vector machine. Support vector machine is widely used in the literature, also in the industry. And this is a non-explainable model. So compared to linear classifiers or decision trees, SVMs generally counted as black box models. It is widely used for binary classification model, and it doesn't return the prediction probabilities as decision trees do. It will only return the class prediction, either default or not default, fraud, not fraud. And similar to the linear classifiers or linear discriminant analysis, as we just described, it searches for the best separation. And this decision boundary, generally called hyperplane, and it is chosen based on the maximum margin or maximum separation between different outcomes of the target variable. So as you see here, let's say this is fraud, and this is not fraud. So fraud, not fraud, same data points. Which one do you think is the best separation? This is the first one, let's say second one, and third one. Okay, I see lots of trees, that's correct. So here, if we use this decision boundary, this separation, we are very close to both points. And it's very possible that we can later come up with a point, test data, just on this side. Model will think that is a fraud case, but it might be not fraud case, since it is looking similar to the not fraud cases. If we are close to one side, we can easily make mistakes for the prediction. But if we are far away from both sides, as in this case, then we are more safe. So that is why linear separators generally do, or while model training, they generally look for the separation, which is far away from both classes. So this is called maximum margin. Terminologies is not that important. Don't worry about that. But just try to understand the logic behind it. Why we are trying to maximize the margin, so that in the future, all the model learns from the training data, it's going to make predictions on the future data. So in the future, there will be a less chance we will make an error. So up to now, all cases we discuss here, as you see, there is a perfect separation. So all points in here are fraud and all points in here are not fraud. So they are perfectly separated. However, real data sets are not generally separable. So there might be cases where we have frauds and not frauds on the same, let's say, graph are actually mixed together. So here, I didn't mention, but this is, assume that this is age, this is balance. We use our data to plot these data points, and currently they are perfectly separated. But we can have a case in the real data where we have some, let's say, nut frauds lying here, and we have frauds lying around this region. So that is completely possible, and most of the time that is actually what's happening. So we don't have this perfect separation. There's one question: can you please explain the difference between the three? So these three are exactly the same points are here. These are the points from the data set, but the decision boundaries is different. So this is decision boundary 1, let's say decision boundary 2, and decision boundary 3. As I described in the previous slides, there are lots of ways you can obtain these decision boundaries. And when we search for the best one, when we're building the model, we check the separation between classes. So this one has the highest separation. So as you see, the distance, which is shown by this light yellow area, is maximized here. On the other hand, while the distance from the fraudulent cases are maximized here, we are very close to the not fraud cases. On the other hand, in here, we are close to both sides, very close. The same graph, only the decision boundaries are different, and that is the actual search or building process of support vector machines. It is trying to find the maximum margin from both classes. And what we were discussing, in real data, we don't have this perfect separation. The classes might be kind of mixed, as in here we have blue dot close to here and red dot close to the other side. So we may not find the best separation where we are far away from both regions. In this case, we are trying to find the separation which actually allows us to make some mistakes, but still from the majority of the points, as you see in here, majority of the points are here and here. This decision boundary is far away from the majority. So we can make errors while searching for the best decision boundary or best separation, but at some point we may not find the perfect one. We allow model to make mistakes, make errors, but still we are far away from the majority. Okay, so this is called soft margin classification. So we can make errors. Errors are possible during model building. So models, when we build them, they are not always trying to find the best or, let's say, zero error separation. We allow model to make mistakes. The important part is to be far away from the majority of the points. Okay. And in some cases, it might be completely actually mixed. As in this case, we have red squares just in the middle and green dots just surrounding these red squares. So here it's not possible to find a decision boundary, right? We can't, if we draw this, then we will have lots of errors. If I draw this, again, there will be lots of errors. When we have such a complete mix of classes, this is called nonlinearity. So points are not completely separated. They are mixed. They are distributed nonlinearly. Support vector machines are quite powerful. It can apply a trick which is known as kernel trick. We will use this terminology during our workshops, therefore I mention it here. What does it do? It transforms the whole data points. As you see here, it is two-dimensional. It transforms the whole data points to a higher dimension and search for the separation in that higher dimension. So during workshops, this part will become much more clear. We can select the kernel as a decision analyst. You can decide whether you are going to build a linear SVM. Linear SVM uses a decision boundary like this one, or whether you are going to use the kernel trick to transform it to a higher dimension and search for the separation in that dimension. So this is one of the, let's say, parameters you are going to set during model building. The reason I'm explaining this, SVM can handle non-linearly separation in the data points. On the other hand, linear classifiers, the other linear classifiers may struggle with it since they use linear decision boundary. Okay. And the final model we are going to discuss today is logistic regression. Logistic regression is widely used again for binary classification problems such as fraud, not fraud, or churn, not churn, cancer, not cancer. Instead of returning the class prediction, whether it is a fraud, not fraud, it returns the probabilities. So it doesn't return the prediction. You need to have additional step to identify the class. Basically, we use 0.5. If the returned probability is greater than 0.5, it will be predicted as the main interest. Generally, it is like fraud. In fraud prediction, our main focus will be on frauds. And when logistic regression model is built, it will return the fraud probabilities. And if it is greater than 0.5, you are going to change it to a fraud class. If it is less than 0.5, we take it as not fraud. So natively, it returns the probabilities. And it uses, again, a decision boundary, linear decision boundary, which is the combination of the features from our data set. When we obtain this decision boundary, it uses a transformation to obtain the class prediction probabilities. And this transformation is done with the sigmoid function. We are not going to the details. You don't need to worry about this. But basically, the main advantage of logistic regression, you will obtain the class prediction probabilities, and it will be your decision to assign the class. Instead of using the default threshold, as I mentioned right now, 0.5, depending on the business case or depending on the data mining problem, you can change that threshold value when you assign the final class. So let's see an example. Here we have a data set like whether the medicine will be effective or not. So this is our target variable. And these are the independent features. When we build the logistic regression model learns between the relation of the target variable and the other features. And the decision boundary is similar. So let's say W0 plus W transpose X. So it is trying to identify what should be the values of W's during the model building stage. And then when the test data, unseen test data comes, it will take the test data, and when we use the built logistic regression model, it will return the probabilities. And these are the probabilities of medicine being effective. So probability, medicine effective. Yes case. So for instance, for the first patient here, the medicine would be effective with probability 0.45. For the second patient, it is effective with probability 0.96, and so on. And given these probabilities, whether the outcome is yes or no, here we have categorical outcome, we are going to do a simple rule. By default, threshold is set to 0.5. This is default threshold. If the probability is less than the default threshold, we are going to predict it as no. If the probability is greater than the default threshold, we are going to predict it as yes. But as I mentioned, as the user, you will have the flexibility to change this default threshold. Any questions up to this point? Let me see. There are some questions on the chat. Would you say this is similar to the linear classifier and the only difference is that SVM is an ML method? So I think you are discussing this separation. SVM is also a linear classifier, but due to the kernel trick, it can also handle nonlinearity. So it can be used for nonlinear models as well. The separation between SVM and other linear classifiers is that they use a different objective function. So in SVM, when we search for the maximum margin, we calculate the loss based on the errors in this margin. In the linear classifiers, on the other hand, the error calculation is different. So both models have looking for a linear decision boundary in the linear SVM case, and both of them are trying to maximize the separation between classes, but they have different type of objective functions, since these are mathematical models. SVM is more powerful due to some assumptions, and it can also handle nonlinearity by transforming the data. And one question, I hope this is clear, Jimmy, and one question from Manoj, but as if the data is perfectly separated and the decision bundle is very close to both of them, then why is the possibility why that the error will be occurred? Probably you're asking this. Why? So if the separation is, let's say, whether I can clean all of it, let me see. Is there a way? Yes, all ink on the slide. Yes, this is better. So we search for this maximum margin with the hope that when we have the test data in the future, we don't make any mistakes. So if we use this, these points are all from the training data. We don't know the test data, or we don't know the future. Test data isn't used during model building, and we don't know future points. So let's say we have a point around just here. And this is test point. Or let's say in real life, future point. If we use a separation close to both sides, then we can make an error. Very easily, we can make an error. So this will be classified as blue, but it is very close to the red ones. Probably that point is around somewhere here. So if we use the maximum separation, actually we can classify it is correctly. If we are close to both sides or one of the sides, then there will be a very high chance in the future the model can make an error. By staying far away from both sides, there is a much less chance it will make an error. So that's the reason they are always looking for this maximum separation between classes. I hope this is clear. Okay, I don't see any other questions, but please feel free to ask. Okay. So you may ask which model to use, which model is the best. And there is a really good word from George Box, from statistician George Box. All models are wrong, but some are useful. So these models are actually representation of the real world, but they make assumptions. We don't use all of the, if you consider customer churn problem, we don't use all of the information about the customers. Or if you don't have the, let's say, market information or competitor information, when we build the model, it will be unaware of the uncertainties in the entire world. So that's the reason models are generally wrong when they make a prediction. There's a high chance they will make an error. We don't expect to be a model to work with 100% accuracy, and 100% accuracy on the training data is actually dangerous. We will discuss it next. But models help us, even they make errors, even they make wrong predictions, they can help us to make better decisions, and they will also provide understanding of the system. Like in the information gain workshop, we discussed that models can return important features, which will shows about the customer behavior, or which gives information about the business itself. So no model is completely accurate. There will be always things we cannot measure or account for perfectly, like human behavior, random events, external shocks from the competitors, or COVID. COVID changed everything. But this doesn't mean they are not useful. In fact, a good model can help us to make better decisions even if it is not perfect. It can highlight the key drivers in the, let's say, or patterns in the data, reveal relationships, and allow us to run what if scenarios. So you can check, okay, what happens if our customers are only old customers or only high income customers, what the churn behavior will look like. So you can always use models to drive some important information about the business. And when we move to the, let's say, evaluation, you will see that we will not always have the 100% accuracy. We will see models are making mistakes, and we are trying to actually choose the model which is best for the business and based on the, let's say, data mining objectives. So we discussed linear classifiers like linear discriminant analysis or logistic regression, or you also will learn linear regression, which is not a classifier, but the whole idea is the same. It uses combinations of the features to predict the outcome. So linear classifiers are easy to use. They are easy to interpret. The coefficients of the model, the ones we discussed, like W0 plus, sorry, this is not transport, W1 x1 plus W2 x2, Wn xn. So these coefficients actually shows the importance of each feature in your data set. So here we have H, whether they positively affect the outcome or whether they have a negative impact on the outcome. Balance is x2. Let's say this is gender. And each of the feature in the data set, if you use them, you'll have a coefficient, and those coefficients can be used for interpretation. What is the contribution of that particular feature to the prediction? So they are interpretable, they are easy to use, but they have strong statistical assumptions. They assume points are normally distributed, and they can work well linearly separable data. So as I mentioned, SVM can handle nonlinearity. On the other hand, linear classifiers, they struggle with nonlinearity. SVM, on the other hand, is much more powerful, but it is not easy to understand since it is a black box and we can't directly interpret the prediction it is making. It doesn't return the class prediction probabilities as in the decision trees or as in the logistic regression. It can handle nonlinearity, and it doesn't have any strong assumptions about the distribution of the data set. It doesn't assume data set is normally distributed. It can handle large number of variables, so you can have a data set with hundreds or let's say 500 features or variables, but it is quite slow when we have large numbers or large data sets. So it might be computationally challenging. And in that case, sampling can help to build the SVM model. Decision trees, on the other hand, they are rule-based methods. As we've seen in the last workshop, they can return prediction rules, so easy to understand, interpretable, and they can also handle nonlinearity. They don't assume linear separation since they divide the data set based on the splits, which is obtained from the feature itself. So we can have a very fine split where we can only include one particular sample in the data set. That's the reason they can work with nonlinear data. They can work with categorical and numeric data types at the same time. If you are not using Python, if you are using another language, you don't need to use encoding. You can directly build the decision trees. But feature split, so which feature to split the data, has an impact on the performance. For instance, in the previous workshop, we've seen that overtime has a huge impact, and we start splitting based on overtime. But if you choose another feature, the whole prediction process is going to change and the performance is going to change. So features to split the data affects the performance of decision trees. So let me quickly check the time. I think we are over the time. Just this slide and then I will end the lecture. When we decide which model to use, we should not only consider the accuracy, we should also consider the interpretability versus complexity. So one of the most well-known trade-offs in machine learning is black box models versus interpretable models like decision trees or linear classifiers. And this trade-off is due to the accuracy, while black box models can be more accurate since they can handle the complexity in the data set, but they are not easy to understand and they are not easy to interpret. On the other hand, as we've seen in the class, decision trees can be explained, and linear classifiers as well. By using the coefficients, we can identify which particular features has an impact on the prediction. So we can understand from decision trees, linear classifiers, why a prediction is made, and this transparency helps us to build trust, especially in businesses or policy, let's say, settings where decisions directly have an impact on the people, like in healthcare. When you predict whether the patient has cancer or not, you need to understand how this decision is made. And the best example is given by IBM's Watson supercomputer. This is a huge fail in IBM side. They use a supercomputer to predict whether the patient has cancer or not, and they also use this algorithm to recommend treatment for the patients. And after several applications, it has been very severe impact on the patients, and it has been scrapped. And the reason was the medical professionals, they couldn't understand how the supercomputer is making recommendations. And later it has been revealed that the training data wasn't representative enough. So it didn't cover all patients' domain, and the treatment recommended was unsafe for the patients. So from that perspective, if the machine learning model has a direct impact on human lives, or if it is working on a very sensitive business subject, the users may want to understand how prediction is made, and by sacrificing slightly from the accuracy, it might be better to use more interpretable model. So we should not only consider from the model performance, we should always consider more from the business side, what the managers would like to achieve. Whether they would like to have an interpretable model, or whether they would like to have a black box model which works with higher accuracy. I think I am going to end at this stage, and during the workshop we will continue with the overfitting problem. So if you have any questions, I would be happy to take. Let me check the chat box. Okay, I answer this question. So to sum up, we will choose to use linear discriminant when the data look like quite separate, SVM when the data look very jagged, and we will need to kernel triple deal with this. Okay, which model to use? Unfortunately, you can't illustrate the data. This illustration is only possible when you have two-dimensional data. Most of the time, as if I go back to this slide, your data is quite complex and it's not easy to illustrate. So what we do, we build several models, and we generally choose one of the interpretable models like decision trees, and other strong models like SVM. We will discuss more of these random forests and GBM in the upcoming workshops. So we built these several models and then observe their performances to decide which one to choose. But if the business requires you to only build an interpretable model, and then you can directly eliminate SVM or more complex models like deep learning, neural networks, and focus all on the decision trees and logistic regression. So we will always build several models to compare the performances and understand. I hope this is clear. And one question, for what kind of issues would you say is SVM used in real life? I mean scenarios where it doesn't matter, that is a black box. Good question. For instance, in the fraud prediction cases, generally more powerful algorithms are used, like random forest SVM or deep learning models. It depends on the business, let's say, expectations. But generally in healthcare, black boxes can be quite dangerous, since you may want to understand the decision-making process. But if the decision-making process is not that much matter, like maybe credit risk prediction, or it has a very financial impact, the wrong decision, if the accuracy is very important, like in the fraud prediction, then powerful machine learning algorithms to prefer is much better. For instance, spam mail. So we will see that scenario in the upcoming lecture, where we are going to predict whether the email is spam or not. In that case, understanding how that prediction is made is not that much important. So SVM or other machine learning, black box machine learning techniques is much more useful. Okay, one question from Ashir. Can you please briefly explain the logistic regression? So logistic regression is also a linear classifier. Similar to linear discriminant analysis, it has trying to search for the best decision boundary to separate the outcome, like fraud, not fraud. But different from the other linear classifiers, it returns the probability of being from a particular class. So it doesn't directly return over this line would be blue and under the line would be orange. It will return the probability of being blue and probability of being orange. So that's the main difference. And in order to return the probabilities, it uses a transformation. This transformation is done with the sigmoid function. I will not go into the details, but this will help to, given the decision boundary, like W0 plus W1, feature 1, W2, feature 2. Given this decision boundary, this is an equation. It is actually returning a value, a number. It uses the sigmoid function to obtain a value between 0 and 1. So it has this two-stage transformation. After identifying the decision boundary, it returns the prediction probabilities, and we use that prediction probabilities to identify the fraud or not fraud, or assign the final class. But this will become much more clear when we implement this next week during our workshop. But the whole idea is the same. It searches for the best separation between classes, but instead of returning the class directly, it applies a sigmoid function transformation, which will return the prediction probabilities. I hope this is clear now. Okay, I think I answered all questions. I couldn't see any other notes. Please check the chapter 3 from your book. It describes the linear classifiers well, and I think, if I'm not mistaken, there's a section on decision trees as well, so it provides lots of examples, and it may help you to understand better the concepts, but it will become much more clearer when we start to implement these during the workshop and how they work. So thank you all. Thank you for your participation. I will see you next Monday or Tuesday based on your workshop groups.